lecture of this very quick and superficial introduction to cosmology, but I hope you get at least an idea of cosmology at some very basic facts in cosmology. So just to recap, something we did last time was to study how the different fluids in the universe would evolve with time, how the energy density of different fluids evolve with time, and then what we saw is that if you have, so when I mean fluids, I mean perfect fluids with different equations of state. So we saw that basically we can divide into two broad classes, the fluids that describes the universe, non-relativistic fluids and relativistic fluids. And the cosmological constant is we also showed last time that we can describe the cosmological constant as it was introduced by Einstein in 1917 as a perfect fluid with an equation of state where the pressure equals minus the energy density. So what we saw last time is that we can plot how the energy densities of different fluids evolve with time in the universe. And I hope you get from these lectures that when I say time in the universe, there's different ways we can parameterize time, different clocks if you want. So you can use the real time, you can use the conformal time, you can use redshift, you can use the scale factor. All these different variables are different proxies for time in the universe. So I hope that's clear. So then what we saw last time is that we can make a plot of some proxy of time, which is the scale factor of the universe. But I use the log of the scale factor of the universe, A. So A, we saw before, is what describes the flat Friedmann-Lemaitre-Robinson-Walker metric. And here I can put the logarithm of the energy density of different fluids. And then we can see what happens for different fluids in the universe. And this is something we saw last time. So suppose we are here. So this is today. And if you remember today, what is the value of the scale factor today? 1. So log of 1 is 0. So this is today. And today, we know that, so let's start with a component of the universe. Let's start, I don't know, with radiation. I think radiation is here, let's say. And when you go back in time, back in time means the universe contracts and the energy densities increase. And the energy density in radiation increases with the power of A to the 4th power, so it decreases with A to the minus 4. So if you go back in the story of the universe, it increases with this power of 4. So it's something like that. I always draw this wrong, but so this is, suppose this is 4. And then if you have matter, cold dark matter. So cold dark matter today, we know it's bigger than the energy density in radiation. So later on, I'll tell you what these values are, okay? But this is just to give an idea. So when you go back in time, what happens to the energy density in non-relativistic matter? It also grows, but it grows less than radiation. It goes with the power 3 instead of power 4. So at some point, they will cross each other. I'm sorry, this is wrong, right? No, this is right. No, this is wrong. Sorry, this is wrong. So let me erase this and write this again. So this is radiation. This is matter. And this is right. So in the past, what happens in the past? Which component is dominant? Radiation. So that's why the universe is hot and dense in the past. And then the elephant in the room is what we call the cosmological constant. I don't know how to draw it. I draw in green, maybe. So what happens to the energy density of the cosmological constant? it stays the same. So this is the cosmological constant, something like that. So we know that today, sorry, this is supposed to be a straight line. Sorry about that. So today, the cosmological constant is the dominant component of the universe. Very good. So this is what we saw last time. So there are interesting periods here in the universe, and this is a time, for instance, what happens at this scale factor here, at this particular value? That's when the energy density in the cosmological constant equals the energy density in dark matter. So I call this, I don't know, I call this A lambda, which is the scale, the value of the scale factor where the energy density in cosmological constant starts to dominate. And then there's another interesting time in the universe, and this is when the energy density in radiation equals the energy density in cold dark matter. And this is called equality. This is the usual name that people give. So this is the equality time when the energy density in radiation equals the energy density in cold dark matter. So this is interesting, and the cosmological constant is something strange because, you know, if you look in the past, it's completely negligible. So it's not important at all, and only becomes important, and we are going to compute actually when it becomes important today. Okay, so we're going to compute these things here. Very good. So now we can start the lecture. Right, so everything this we saw. So again, this plot here, this very simple plot, it's one of my favorite plots. It tells you that in the early universe, the dominant component is radiation. So, and the universe was very dense in the beginning, okay? So the universe was dense and hot in the early times. So we derived how the scale factor changes with time also last time. And what I'm going to do today is to talk about these components of the universe, what we know about the universe. So if you're, okay, just one comment. If you're looking at your notes, you see that there should be a number 12 here, not 13, because I'm skipping one part. I will come back if I have time. I'm skipping inflation. I'm coming back if I have the time. But I want to do something fun today. So let's talk about what is the recipe for our universe. So what I mean by recipe, it's really a recipe. When you're cooking something, right? You put, I don't know, one kilo of rice, 1 liter of water, some oil, and then let it cook. So those are the ingredients of the recipe. So what is the recipe of our universe, right? So what is the universe made of? What do we need to characterize the universe? So that's what we're going to talk today. So first, we're going to start the Friedmann equation. Just to remind you, this is the Friedmann equation. 8 pi g over 3 times the total energy density of the universe. That's what we derived also in one of the lectures, okay? Now, up to now, we have forgotten the possibility that the universe has a spatial curvature. This has many questions that you asked me about this spatial curvature of the universe. And this equation was derived under the assumption that there is no curvature in the universe. Now, if there is curvature, spatial curvature in the universe, the metric has to be changed, and that's easy to do. And this equation actually changes as well. So I'm just going to write what we didn't do in these lectures. What is the contribution of spatial curvature in this equation? And this is the answer. And I'm just going to write, because we're going to forget it very soon again. And this is the effect of curvature. This is scale factor. And again, this you can get from the, you have to modify, it's not difficult. Modify the Friedmann metric, Robertson-Walker metric to include curvature. That's not difficult. So this is the effect of curvature. This k could be 0 plus or minus 1. And then I'm going to introduce something that that's a definition we use very often, which is something called the critical density of the universe. So what is the critical density of the universe? Critical total density of the universe. So the critical density of the universe is defined in such a way that the curvature is 0. That's the definition of critical density. So the critical density is just when the curvature is 0, which means that the critical density today is just Hubble, the Hubble constant today square times 3 divided by 8 pi g. So this is the definition of the critical density, and I put the index, the upper index 0 to say it's today, okay? Because it changes with time, because the Hubble changes with time. So when we say that the universe has no curvature, or very close to 0 curvature, it means that we are in a situation where the total energy density of the universe is the critical density. Okay? And it's really interesting. This is an exercise you can do. Just compute this number, because we know what is the Hubble constant today. 70 kilometers per second per megaparsec. There's some small certainties there. And you can see what is the average density of the universe today. If you do this, you get that the average density of the universe today, it's equivalent, more or less, to 5 protons per cubic meter. Yes? So this is included in the curvature, in the scale factor. Yeah, again, this is all included in here, in this factor. So only this signature of the curvature, that's a constant. And this can be 0 plus or minus 1. So, yeah, so I was saying that if you compute, again, you can really compute what is the average density of the universe today. And the average density of the universe today, believe me, you can do it, is around 5, is equivalent to 5, the mass of 5 protons per cubic meter. So it's really small. This is the average density. So we are far, in this room, we are far from being the average density. Okay. So, yeah, questions? Yes?
There's some name for the point of neutrality of the line of cosmological constant and radiation.
No, because here the dark matter is more important. But we can compute everything, so it's not really. So what is important is what is the dominant component. So here the dominant component starts to be dark energy, or lambda, and here the dominant component starts to be radiation in the past. Yes? I'm sorry. I should. So this is matter. This is radiation. And this is the cosmological constant. It's non-relativistic matter, general. So any non-relativistic matter behaves like, the density goes like a to the minus cube, a to the minus 3. A to the minus 3, because just think of matter, non-relativistic matter in a box, and if you expand the box, the density decreases as a volume. That's why it's a to the minus 3. I'm sorry, this is non-relativistic matter. So any non-relativistic matter, be it dark matter or be it atoms, etc., the density behaves like that. Thank you. Any other question? Yes. Well, if you can observe the average quantity of matter in the universe and measure it, then it should match. But this is a theoretical thing. No, we don't have the estimation. I mean, we can estimate observationally, but there are lots of uncertainties. And in fact, it was not clear in the past whether or not the universe was in the has a critical density. So people thought, oh, maybe the universe is not at a critical density. What would happen if the density were smaller than the critical density? The curvature would be negative, which means that the universe would have this saddle shape, okay? And in the past, when people were trying to do what you were saying, they say, oh, we don't see enough matter, and the universe is open. That was the usual names we used in the past. The universe was open, no? The saddle shape. Now we know from measurements, but indirect measurements from the cosmic microwave background, for instance, that we're very close to this. Or the contribution of this is very small. Because we can measure the expansion rate, and we can measure geometrical factors in the universe. So if you look at the literature in the last century, in the late last century, you see that this not confusion, but the lack of experimental data led people to think, oh, maybe the universe has less, the energy density is less than the critical density. Okay? Yes, so A doesn't have units, yes. So there's something wrong with the units here. So I have to check the units here, sorry. There's some problem. You're absolutely right. Huh? Yeah, I have to check the units. There is a problem with the units here. And so take this with a grain of salt, okay? So let me write here, there's problems with units and I have to check it. So there may be some factors here with some dimension which is related to the sizes of the universe and things like that. So we have to check this thing. Thank you. Yeah. So I check what is wrong with this. But the idea is this, that you can include the effect of curvature as an effective density, and this should have dimensions of energy square. And so we have to see where this dimensions comes from. Sorry? No, it's not that. I think sometimes the scale factor has, you define it as having some dimensions, but I'm not doing this, so there should be some dimensions I have to correct. But it will not matter because what I'm saying is correct, that this curvature term is negligible. Okay, that's the important message to get from here. Yeah, that's what we was saying, but no, it's not that. No, no, it's the matter of definition of the scale factor. Some people define the scale factor with dimensions. So I probably looked up at a different definition of the scale factor. So it's not natural units, okay? So yeah, so again, there is a problem with units, and there's a radius here of the universe that has to be in here somewhere. But that is not the main point. The main point is that the curvature contribution is negligible, and we know that. Okay? So now we can do a decomposition of the energy. So this is the total energy of the density of the universe. And then the recipe is, okay, what is the universe made out? What is the composition of the universe? So this is a sum over different components of the universe. So what are these different components of the universe? So basically it's matter, radiation, and the cosmological constant. Okay? So, so we can write the Friedmann's equation the following way. Sum over all the components of the universe. Okay, it didn't do anything. But now I will write this in terms, I use the critical density to write this as, I'm going to substitute 8 pi g over 3 by the critical density at 0 divided by h times h squared. So this I can write as h naught squared. See if I didn't make any mistake. Rho critical. I can write like this. Is this correct? I didn't make any mistakes, right? And now I can define what is called the ratios of the densities, or the density fractions. These omegas are density fractions. And I will define the omegas as being the density fractions. So the ratio of the density of the component I divided by the critical density. Okay, that's the name that we give. Yeah, so this depends on time. Okay, at this point is depending on time. Okay, so the sum of these components is 1 at every time. That's independent of time. Is that okay so far? So the critical density changes with time. Okay, when I put 0, it's because it's today. When I don't put the index 0, it's because it changes with time. So now what I can do is write this equation as follows. So this is the Hubble constant square. And here, for each component, so now I will say that each component has an equation of state. And I assume the equation of state to be constant. So each component, I can write the density as this, minus the equation of state, basically. So all I did here was to write how each component changes with the scale factor. So we saw this last time. For instance, matter, non-relativistic matter, the equation of state is 0. It goes like a to the minus 3. Radiation, equation of state is 1/3. It goes like a to the minus 4. And cosmological constant, equation of state is -1. It's a constant. Okay? And now this is the fraction at 0. So I can write this as h0 square that's it. That's the Friedmann's equation in terms of these variables, which are the components of the universe. So if I give you the components of the universe today, you can solve this equation. Okay? That's easy. All right. So now if you only have matter, which is matter and radiation and cosmological constant, I can write this even more explicit. So this is gamma omega of matter today. So the energy, the fraction of density in matter divided by respect to the critical density. Radiation today, a to the minus 4, plus cosmological constant. That's it. If those are the only components. So I leave you as an exercise, a simple exercise, to show the following. So consider a universe so this is a simple exercise with only matter and radiation, so no cosmological constant. And assume that the energy density of matter at some equality value equals the energy density of radiation, this equality value of the scale factor. Then show that the Friedmann equation, if we only have these two components, reduces to this. A minus 4, A plus A ec. So that's very simple, but that's instructive. So now we are ready to see what happens in our universe. If I give you, basically if I give you these components here, you can describe how the universe behaves in time. Okay. So now I'm going to give you the recipe for our universe. So what characterizes our universe? So our universe is well described by a model, which is called now the standard cosmological model. Which we already talked about it. And this model is called Lambda CDM. So what is a Lambda CDM model? It's a model where the universe has a component which is dark energy and a component that is cold dark matter. And the cosmological constant is responsible for the acceleration of the universe. So the question is, how many parameters? So every model has a number of parameters, right, that you have to fix. Once you fix these parameters, the model is determined. So what are the parameters we have to define, we have to fix, measure, and in order to characterize the Lambda CDM model? So there are a few parameters. So what are the parameters of the model? Yes. So first, the amount of matter in the universe today, the amount of cosmological constant in the universe today, the amount of radiation today. Yes. Now, these three are not independent because what the standard model is actually a flat, spatially flat Lambda CDM. Of course, you can add curvature and check whether or not curvature is small. And that has been done, of course. So these are not independent. So from these, you choose two. And then the expansion rate today. Yes.
Can you explain briefly what is the Lambda CDM model?
What is the Lambda CDM model? So I think I mentioned this maybe in the first lecture. What is the cosmological model is based on general relativity, on the standard model of particle physics, on the existence of another species of particles which we call dark matter, and that they have to be non-relativistic, cold dark matter, and the fact that the universe, we know the universe is accelerating, and what is responsible for the acceleration of the universe is something called the cosmological constant, which I described in the last lecture. Is that clear? There's one extra piece of information that I'm not, maybe I'll talk later, which is there's another ingredient, let's say, of the standard cosmological model, which is inflation. So there's a period of the universe which is way up here in the beginning, where the universe starts, had a very large exponential expansion phase, which was very short. I think I mentioned inflation, but I didn't. Yeah. So yeah, so this is what is important for the what's called the background universe. So let me just make sure that I have some comments here to make. So this is let me just go back and tell you that from the beginning of these lectures, I told you that we're going to talk about the homogeneous universe, the background universe, unperturbed universe. If you're talking about those of the unperturbed universe, this is what you need. So this is what you need for the unperturbed universe. And even in the case of unperturbed universe, there are some uncertainties from particle physics. So let me just say this again, just to let you know that there are some uncertainties here. So again, this is the radiation part of the universe, right? So what is radiation? This actually I should say relativistic part of the universe. So what makes the relativistic part of the universe? Photons, right? Yes and no. So photons for sure. But there are particles called neutrinos. Neutrinos are very light particles, and they can be relativistic, depending on the mass. So this relativistic part should include neutrinos. But we don't know much about the neutrino masses. We know their light, we know their mass differences, but we don't know exactly what the masses are. So there's a little bit of uncertainty in the contribution of neutrinos to this guy here. And in the following, I will assume that neutrinos are massless, in which case they are always relativistic, and you should include them in the radiation part, because they are relativistic particles. And we know how to include them, yes. That's an open problem. So we try to get bounds on the masses of neutrinos using cosmology, by the way. Right? So that's an open problem. And if neutrinos have masses, and we know they have masses, right? Then they can transition from being relativistic to non-relativistic, depending on the mass. So all of this has to be taken into account. Okay? But for these lectures, I would just assume that neutrinos have zero mass. And this includes neutrinos. And we have 3 neutrinos. That's another assumption. There are lots of evidence that we're only 3 neutrinos. But okay, so we have 3 neutrinos, and for the purpose of these lectures, they're massless. Now, there are 2 parameters that need to be, when you're talking about the perturbed universe, which we are not doing in these lectures, but just for you to know, if you look it up, there are 2 other parameters that you need to consider, which, of course, were not mentioned in these lectures because we didn't need them. They're important if you want to study how structures form in the universe, for instance, from small perturbations. And these small perturbations, they have an amplitude, which is called AS, and a behavior of how intense these perturbations are as a function of scale, which is called NS. And I didn't talk about this because we're talking about the unperturbed universe, but these are parameters that you need also in the standard cosmological model. So basically, you have very few parameters. Let's say 1, 2 from here, 3, 4, 5, and if you talk about neutrinos, maybe 6. So that's amazing. With 6 numbers, in principle, you can predict everything. There's another thing I have to mention here. So when you're talking about perturbations, again, it's important to distinguish matter. So it's important to distinguish cold dark matter and baryonic matter, but only when you talk about perturbations. If you talk only at the background level, they behave the same way, and we don't have to worry about distinguishing them. Now, if you look at how galaxies form, baryonic matter behaves very different from dark matter because baryonic matter can radiate energy, can dissipate. But this is amazing, okay? So very, very few parameters, 6, 7 sometimes, you can describe the whole universe. Okay? So now I'll give you what the parameters are, and then from here we can compute many things. So any questions? Yes. So that's a good question. I put an index 0 here. And when I put an index 0, is to make sure that it's today. Okay? So this is a very good question. These density fractions, this omega, they're functions of time. So in the past, as we see here, the cosmological constant is negligible. So omega lambda in the past is very close to 0. And omega lambda today is the dominant one. They always sum to 1. The omegas always sum to 1. All the time. But the proportions change. Is that clear? Okay, so let's see what the parameters are. So let's start with omega radiation. So again, this has the contribution of photons and neutrinos in principle. So the photons, the energy density of the photons, a photon gas, right? So what determines the energy density of a photon gas? Do you know? There's only one thing that determines the energy density of a photon gas. It's the temperature. It's a gas. It has a distribution of momenta, etc., and frequencies. Again, the frequency is not a single frequency, right? There's a spectrum called the black body spectrum. So what fixes the energy density of a photon gas is only the temperature. If you give me the temperature, I give you the energy density of the photon gas. And we measure the temperature of the cosmic microwave background very precisely. So we know what is the energy density in photons very precisely, in the photons of the universe that comes from the microwave background. So this amounts to, so the photon amounts to something like, I'm not putting the exact numbers, I'm not even putting the uncertainties. I'm just putting the ballpark value. So this is the fraction density of photons today. It's very small. So today, photons are negligible compared to the other components. But they're very important in the past. They're the dominant component in the past. Right? So this comes from the fact that we know the cosmic microwave background temperature. With very high precision, so 2.7, well, I put it like that. Now, if neutrinos are massless, they also contribute. And we can also compute from the history of the universe, we can compute exactly how neutrinos contribute to the energy density of the universe today. And they're also small, but comparable to photons. You know that in each cubic centimeter, there are like 400 photons from the CMB? So this we can compute. Anyways, I'm not going to do it now. So the neutrinos, they contribute, and it's comparable, a little bit smaller than photons because they have a temperature that's a little bit smaller. Again, this comes from relativistic gas of particles, but these are fermions. So there's a difference between fermions and bosons. So if you add them up, the contribution of relativistic particles is around 9 times 10 to the minus 5. So it's very small. So this is a number I need in order to specify how the universe evolves. Then I also need the amount of matter in the universe. And this has also been measured. And it doesn't make a difference, but I put here the contributions from dark matter and from baryons, because we know how to distinguish them, not in the background, but in the perturbations. So this is just to tell you that this is around 0.27, and this is around 0.05. This is measured, okay? So that means that there are roughly 5 times more dark matter in the universe on average. Of course, in our galaxy is different, on this room is different, but on average, there is 5 times more dark matter than baryons in the universe. Okay, so this is around 0.32. So now we know what has to be in cosmological constant. Just subtract this from 1. And what you get is very close to 0.68, right? Yes. Yes. Yes, you should, but they're negligible today. Okay. So with these numbers, we can compute many things in the universe. And that's what I want to do for the remaining of this lecture. So now, with these 3 numbers, we can compute many things in the universe. So that's what we're going to do now. So I call this section Fun Facts About the Universe. So you go to a bar with your friends, and you want to distract them, start a conversation. Maybe not a good idea, but so, okay, I have some fun facts about the universe that I want to share with you. All right, so let's start with this. What is the age of the universe? So you go to a bar, say, okay, what do you think is the age of the universe? So we're going to compute the age of the universe, because we can. So I called the age of the universe TU. Okay? So I think you all agree with this equation here. You agree with that, right? Good. So let's let's massage this a little bit and make a change of variable. So I use an integral not over time, but I want to use the integral over the scale factor. Okay, remember that a scale factor A dot is dA dt. So I can write dt as dA over A dot. And I can write this as dA. So A dot is related to the Hubble parameter, except that Hubble, again, Hubble parameter is A dot over A. So A dot is A times Hubble. Okay. So what is the value of A in the beginning of the universe? What is the value of A today? That's the integral. And what is age? So this is just the integral, 0 to 1, dA over A. And here, I have to see what age is, so I use the Hubble, the Friedmann equation. And if you remember the Friedmann equation, this is age 0 times omega matter 0, A to the minus 3, plus omega radiation 0, A to the minus 4, plus omega lambda square root. Right? So the age of the universe is this thing. I can take the constant 1 over h naught outside this integral. So what gives you the dimensions or the scale of the age of the universe? Yeah, 1 over h0. So what is h0? So this is one of the parameters, right? Oh, I forgot to say that. So the other parameter is H0. And they're very precise measurements in the last 20 years of the Hubble parameter. And there are some small uncertainties, but for these lectures, let's use this. 70 kilometers per second per megaparsec. So this is the usual units that astronomers like to use because, you know, they measure h naught as a ratio between speed, recession velocity, and distance. But if you notice, the dimensions of h0 so is 1/2 the rate. It's a rate. So if I compute 1/h0, and you can do it. So let me just give you the numbers. Okay, so 1 megaparsec is what? It's roughly 3 times 10 to 19 kilometers. And 1 year is roughly 3 times 10 to the 7 seconds. If you put this here, guess what 1/h0 is? It's 14 billion years. You can do it. Just do it. I can do it, but you can do it as well. So this is actually 14.3 billion years. So the only question that you need to solve now is the integral, right? You just need to solve this integral. And this integral is our order 1, believe it or not. So you can use your favorite code to solve this integral. And of course, in order to compute the integral, you need the parameters, the other parameters. The only parameter I used so far is the Hubble parameter. But for here, I need omega matter, omega radiation, omega lambda to solve this integral. And I did that using Mathematica. And if you use the parameters I gave you, this integral equals to 0.95. So when we say that the age of the universe is 4 point whatever billion years, where does that come from? It's basically just the inverse of the Hubble constant, basically. Now, of course, if you change the parameters, you change the value of the age of the universe, and I did that too. So this is for our universe. Now, suppose you have a universe, which we thought before was the case, with no cosmological constant, and everything today in matter. So we had that in the last century. This was called the Einstein-de Sitter model, by the way. Einstein-de Sitter, they got together in 1932 and wrote a 2-page paper where they proposed a model where there's no curvature and no cosmological constant. So this is Einstein-de Sitter. So you can do the integral, and I did, and you get 0.67. So it's smaller. And with 0.67, the age of the universe would be around 9.5 billion years. So we don't measure the age of the universe. When you say, okay, I have the age of the universe is measured to be 14 point, with very precision, right? I don't know what the precision is, but if you look at the papers, you see that. It's not that we measure it directly. It's that we compute it from a model. So there is an assumption here that the Lambda CDM is the model that describes our universe. Okay? Is that clear? Yes. If the model is approximate. So if the model is approximate, you have to give me what is the real model in order to compare. I don't know, right? But the thing is that within this model, there's also uncertainties in these parameters from measurements. And this gives us this uncertainty in the parameters, hey, and the Hubble parameter, in all these other parameters, gives you an uncertainty in the age of the universe as well. Right? And this you have to quote the age. But because of the precise measurements, the recent precise measurements, the uncertainties in the age of the universe are very small. But within the Lambda CDM model. Now, there are some models that are limits of the Lambda CDM model. I just mentioned one, Einstein de Sitter. Einstein de Sitter is the case where there's no cosmological constant and the universe is spatially flat. So there's only matter today. And in that case, the age is 9-point-something billion years, which starts to contradict ages of stars and old galaxies and things like that. So you have to be careful with this. So is that clear? Yes. For our universe, which means these parameters here. This, and that. So the 0.67, thank you for the question, is a universe where there is no cosmological constant and only matter. And this is what was called, is still called Einstein de Sitter model, which I mentioned before. Is that clear? Sorry if I'm going too fast. So I'm comparing, so as I said, in the Lambda, you can take a limit of the Lambda CDM model where we reproduce other models. This was your question, right? In this case, I know how to compute things. So I'm just computing two different cases. And this is the value of the integral only, okay? That multiplies 1 over h naught. Is that clear? No? Okay, more questions? Yes. Yes. Yes, because the universe is always in its critical density. We change with time, but it's always critical density. Okay? Yeah. More questions? Okay, so that was a fun fact, no? You can compute. I always find this great. You start computing the age of the universe with this integral. So you can do it. Okay, another fun fact. What is the size of the universe? That's another question you get in a bar, right? You're talking, oh, I work in cosmology. Oh, really? What's the size of the universe? Yes. All right. First of all, if a person in the bar asks me, what is the size of the universe? My answer is, I don't know, right? Because we cannot have information about the whole universe. Why we cannot have information about the whole universe? Because it had a beginning, and light has a finite speed, and we can only see things that light leads to us. So there's a size, observational size of the universe because of the finite age of the universe. So light only has this amount of time to travel. So that's why the universe has a finite, the observable universe has a finite size. Now, but again, if people ask me, what is the size of the universe, they have to define me what the universe is. If I say, oh, everything. But I don't know the rest of the universe. I only know what I have access to, what I can observe. And that's called observable universe. Okay? So let me ask you, if you're in a bar and you're talking to your friend and say, oh, I know the age of the universe is 14 billion years. And the person asks, okay, what's the size of the universe? And say, oh, that's easy. It's 14 billion light years. Why? Because this is the time that we have, the age of the universe is 14 billion years, and light can travel in 14 billion years. Light can travel 14 billion light years. So that's the answer you would give to your friend. This is wrong. And I tell you why it's wrong. It's wrong because the universe expands. So it takes more time for light to arrive to us. So the question now, this other fun fact, is what is the size of our observable universe? So again, we're going to use conformal time, and space is equal to conformal time, basically. So we use conformal time from the beginning of the universe. I always get confused. From the start of the universe. So I call it eta 0, the conformal time today, is the integral dt over a. Remember that conformal time is dt over a? I hope you remember that. And I will introduce c here, because I put c equals 1. In the lectures, but I want to have a distance, so I put c. And guess what? Again, this is integral in time. I don't want to do integral in time. I want to do integral in scale factor. So the same thing again. This is dA over a dot, which means this is dA over a square h, which is, we know this integral now. This is dA h naught, and the same thing again. A to the minus 3, radiation a to the minus 4, cosmological constant, factor a half. So I can put h naught here. And the size of the universe is given by this factor. Now, guess what this factor is in light years? It's 14.3 billion light years. So this is the factor that you would guess giga light years. But then you have to compute this integral from 0 to 1. And again, I did that using Mathematica. And if you do it for our universe, the integral, where do I write? This integral here, for our universe, is 3.17. So there's a factor 3 difference when you compute this. Again, it's factors 1, but you know, 3. and, and if you use an Einstein de Sitter model, I get 2, basically 2, a factor 2. So what is the size of our observable universe? So there's a radius of 3.17 times 14.3 gigayears. So the diameter of the universe, the size of the universe, of the observable universe, is roughly 2 times 14.3 times 3, which is around, I don't know, something like 90 or something, 88, 85, 90 giga light years. So this is the size of the observable universe today. Again, you're in a bar, you can tell your friends, I know the size of the observable universe. Huh? Right, right. So this is the diameter of the universe. Very good. So let's see what else we can do. So something you can imagine is, okay, so we have these interesting epochs in the universe when dark energy, when lambda, when the cosmological constant starts to dominate the energy density of the universe. And you may ask, when does this happen? Right? So that's another fun fact. It's fun for me, I'm not sure for you. I'm not sure how many friends you're going to lose if you start talking about this. I don't have much time. Oh, I'm over time, right?
Still have lectures, so I'll be easy on you.
Since I'm over time, I'm going to skip. I'm going to skip a few of these fun facts. No, I'm going to go to one that's really fun for me. No, it's easy to compute. You know, when this thing happens, it's very easy to compute. That's not difficult. So I want to talk something that's very counterintuitive. I'm going to talk about the end of the universe. We talked about the past a lot. We never talked about the end. So this is a fun fact. So if you wait enough, right? Time, you just sit and wait until infinity, right? Time goes to infinity. I'm not saying anything very deep. I'm just saying, if you wait and wait and wait, times will go to infinity. What happens to conformal time? The conformal time is finite of the universe. And this is crazy, but this is what happens. So you can compute the conformal time at infinite. And actually what I'm going to do is just subtract the conformal time today, which is this one here, and eta 0. So again, this is just the integral. The same thing that we did here. This integral is 0, 1, right? Okay. Now this integral here, so again, I'm going to do the change of variables, blah, 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 and I get dA over a square h. So it's the same thing. But what are the bounds? What are the limits? 1 to infinity. And age, again. So this is, I can put age not here. And this is omega m, a to the minus 3, omega m, mr, a to the minus 4, plus omega lambda, a half. But for simplicity, you know, today we know that, I'm just for simplicity, you can do it, of course. But for simplicity, what happens today, today and beyond? Today and to the future, what happens to the universe? What is the dominant component? Huh? It's lambda, right? So the universe is expanding. So all these terms are decreasing with time, except the cosmological constant. And I'm starting from today, just because I want to. So today I know that this guy is already dominant. So I can just neglect this, just for fun. So this is C over H naught. There is 1 over omega lambda to a half. Then I have an integral. How much is this integral? One. So it's finite and it's 1. Right? So this is 1. So it means that there is a finite, even if you wait infinite time, conformal time is finite. And you can compute it. And this I can compute it, and I get, what do you get? So this factor here is about 1.2. This is the 14.3 giga light years. So I get 17.3 giga light years. So there's a maximum size to the observable universe because of the cosmological constant. Okay? The only reason this is happening, suppose there was no cosmological constant. This integral would diverge. It's just because of the cosmological constant. So there's a maximum size to the universe. And this is a lot of fun. So now I'm really finishing. So I can write space-time in the coordinates eta and comoving distance. And suppose we are here. So this is eta 0, eta 0. And if you wait infinite time, you'll be here. So this is the infinite time of the universe, which means that today we are here, our galaxy, observing things, and we can see things in our past light cone. Then we wait and wait and wait and wait and wait and wait. The maximum we reach is here. So there's a maximum size of the observable universe. So this is eta at the end of the universe. End of time. This is a good conversation to have in a bar. So anyways, and you can compute this. Actually, you can compute everything. Exactly. So that's it. So, for instance, I tell you something. So this is us today. Suppose there's a galaxy here. Today. We don't see it, right? Because it's today. We'll never see this galaxy. Never, ever. Wow. Okay. So actually you can compute the volume, the percentage of the observable volume of the universe we already observed is 40%. So we already observed almost half of what can be observable in the future. Again, everything is, just to say it again, this is based on the Lambda CDM model, valid forever. So we don't know. So this is assuming that the model Lambda CDM that we have today is valid in the future. This is what's going to happen. Huh? A what? No, it's just there is a limit to what you can see, right? You don't know what you can, no. There's a limit where information can reach you. And this is clear in this plot. Okay, I think with that, I hope you're not depressed. But yes, so the universe is finite. What you can observe in the universe is finite if Lambda CDM is correct. And you can compute that we already have access to more or less 50% of what can be observable in the universe. So astronomy in the future will be very boring. Okay, so that's it. Thank you.